All right, our next talk is semantics for classical controlled quantum communication. It's given by Theo Wang.
Yeah, so hello. My name's Theo, and I'm going to present the work I've done when I was doing my master's in the University of Oxford with Sam Staton on what? Sorry, it does not. Okay. Hello. Hello. Okay. Right. Sorry. Yes. Okay. So I'll be giving talk on how to give semantics for a notion of classically controlled quantum communication. So what exactly do I mean by classically controlled quantum communication? So if we unwrap the terms, quantum communication just means like enabling programs like this, where you're able to send and receive qubits. And classically controlled just means that like your notion of communication is compatible with the things that you want in quantum programming languages. Especially you'd want to, specifically you want to sort of be able to classically control in the sense that you want to be able to measure some qubit and then perform like a send or receive based on the measurement outcome. So why are we doing this? Well, this thing has clear applications in distributed quantum computing and like sort of giving semantics for quantum protocols. But importantly, unlike the prior works that we have, or like the other works that you'll see, I think, in this session, that mainly focus on distributed quantum computing, meaning that they'll allow for different processes, I'll only talk about like a local sublanguage of these languages, meaning that I will only talk about like one process essentially. And how we're going to do this is by kind of following a roadmap that's very very classical thing to do in programming languages, following the algebraic effects literature. So we'll consider like three types of semantics, like algebraic theories, operational semantics, and denotational semantics, and try to sort of relate them. And yeah, and like sort of ideally get like loads of insights when we do so. So right. I think it's useful to start with the formalism. So exactly the same triangle, but for qubit quantum computing, so without communication. So our starting point is the algebraic theory for quantum computing, so qubit quantum computing that was given by Sam Staton in his POPL 2015 paper. So that algebraic theory is given as like a so-called parameterized algebraic theory, meaning that you can kind of understand it as like a tool for axiomatizing notions of computations that depend on parameters, so in this case, qubits, and it's given in terms of like operations and equations. So an operation can be kind of thought about as an interface, if you will, and like equations can be thought about as like assumptions that you make on these interfaces. So the form of operations for parameterized algebraic theories looks like this. So like an operation here, like of this form says that it's an operation that goes from p parameters, or takes p parameters, if you will, p qubits, and performs a classical choice like between those k branches. And then like if it chooses branch I, then it sort of gives you mi qubits. And in the case of quantum computing, we can kind of like very easily define a couple of operations like this. So like creating a new qubit at 0, we just set it like this, applying a unitary, like arbitrary unitary, and doing a measurement. And this would be we set it to be like a computational basis measurement. And like here, it kind of intuitively says that like it's an operation that consumes a qubit and does a classical branch, and like that qubit is like gone, and you kind of choose between like the two branches. So from these operations, you can like kind of generate terms using like this typing sequence, which is where like a term C that is typed like this, it depends on p parameters, or if you will, p qubits, and chooses between one of like the k outcomes, and like sort of gives you mi qubits if it chooses the ith outcome. So you can kind of write the terms like this, where you have like for example, the new qubit thing would essentially create a new qubit at 0, bind it to Q, and then continue with C. And the rest is kind of like similar. And you can create terms like this. And moreover, you can create equations to sort of like specify assumptions that you make in your algebraic theory, in the sense that like you can kind of assume that certain terms are equal. And this sort of allows you to axiommatize some notion of like program equivalence. And finally, because we're talking about interface, we can instantiate it with what we call models. And like a model should be like a model of a term C can be defined as like this map from like the interpretation of P parameters, so if you will P qubits, to like a classical choice or a sum between like the MI qubits, essentially. So it so happens that if you take like Selinger's sort of very standard QPL model, essentially, like then you get a fully complete denotational model for like this algebraic theory. Fully complete meaning that, so first of all, it's sound, so every equation holds in like the actual denotational semantics, and like the other way around also holds in the sense that if something is true in the denotational semantics, then it's derivable with this algebraic theory. So there is like this very special feature here that like I'd want to sort of emphasize on for those who are not that familiar with quantum computing, which is like how classical branching is actually represented. And importantly, it's kind of represented by like the computation variables here. So like the continuation that you choose corresponds to like the classical branch that you're on. So like the takeaway I want to get from this slide is that we kind of only keep the classical information that's in the computation variables. Yeah, I'm sorry, like I didn't know that the room will be like this. So we only keep like the classical information in like that's like in the computation variables, and we discard everything else. And you can see this by considering these two operations, which are like kind of so they're essentially the same thing in the sense that they both perform a measurement and like computation basis measurement, and just reinitialize like a new qubit that like has the outcome of the measurement, so like a non-demolition measurement, if you will. But the difference being that on the left, like you kind of distinguish between the two continuations, so the two branches, whereas like on the right, you only have one branch. And what this happens like denotationally, because that's kind of easier, is that like on the left, like those two branches kind of like stay there, and you kind of represent it in your map as like a tuple, if you will. And like on the right, you kind of discard this classical information. So you would sum over like the value you get from the two branches. Right. So far we get an algebraic theory and the denotational semantics such that they're related to each other in a very nice way. So I find it pedagogical to kind of see how we can get an operational semantics from it. And it really isn't as complicated like as it might sound, because the operational semantics itself is kind of standard. You can give like a configuration that looks like this, where you have a quantum state, you have like a where you have a tuple of like a quantum state and a quantum program, and like you kind of just run the program. Like there's nothing too complicated. And the way you would define a program equivalence here, such that it's very much related or exactly the same thing as a denotational one, is can kind of be done by just constructing the denotation mathematically from the operational semantics. And that's kind of a standard thing to do. And the way you see this is by looking at this example, where it's exactly the same example where you have on the right, like on the previous slide, where you sort of merge the outcomes here. And you can see that like if you look at like the execution trace of the operational semantics, like you kind of have more classical information that you'd want, in the sense that like the two outcomes, measurement outcomes, where like the two measurement outcomes with the same computation variable are not like merged together. So all that you have to do is really to merge them together by doing a weighted sum over like these states, like by the probability of like reaching that state. So it's just something like this. And this generalizes. You can, for every computation variable, like the denotation of C, the component of the denotation of C at that computation variable applied to an initial state rho is the same thing as like a weighted sum over all the final states of the, by the probability of reaching that final state from the initial state and like ending at the, like at the computation variable, sorry, at the computation variable x. And as a corollary, you can kind of just define your notion of program equivalence like this, and it will be exactly the same thing as your denotation equivalence. Right. So here's what we have now for qubit quantum computing. There's no communication yet. And what we're going to do now is try to see how we can extend this triangle, but for the communication case. So this is what we're going to do. I'm going to start with an algebraic theory because we want to start with the interface essentially before and and the assumptions we want to make on it before we try to look at how we implement it. And then we'll give an operational semantics, and from it we'll derive the denotational semantics. We're kind of going the other way around this time. So how we specify an algebraic theory for communication is not magical. It's just like from the thing with computing, you add two operations, input, output, input sends receives a qubit, output sends a qubit, and you add equations. And like there are actually equations that are non-trivial that you can add. But so first of all, like you don't want input and output to commute with each other because your inputs and outputs might have a causal dependency with each other. And but you do want input and output to commute with local operations. And like it's kind of deeper than it sounds because so intuitively, if you like sort of do something on the qubit and then like send another qubit in parallel, then these two things should commute. Like you shouldn't have like the order of that happening shouldn't matter. And in fact, this is actually crucial to sort of like have some notion compatibility with quantum theory in the sense that, sorry for the string diagrams, by the way, but in the sense that you can kind of like model, like prove within the algebraic theory, like equalities like this, where if you have an EPR pair and you send one end of it and discard the other end, it's the same thing as like sort of pulling that discard back, and then so it kind of becomes a maximally mixed state, and then sending that maximally mixed qubit. So right. Now let's see how we sort of develop an operational semantics that will soundly implement our algebraic theory. So the idea is kind of not very complicated. It's very standard. So because when you have I/O, you want to define like some notion of environment and a way of interacting with the environment. And the way we do this here is by defining a quantum stream. So a quantum stream, you can think of it as like a state machine. So like if you ask for an input, it gives you one. If like sort of like if you're given an output, it consumes it. Like the actual formalism goes as follows. So like the state of your quantum stream is this thing. So it's like just a string of in, out. It kind of says like what inputs and outputs have happened. And the stream itself is a tuple where like Q of sigma for every state sigma is the shape of the current hidden state. And for every sigma, you also have a way of like evolving the the stream state when given input or when like sort of given output. So your global state, so there's when running the program, like your state will look like this, where you have like some side that like this bit as the program state, and this bit that's kind of like the stream state. And what like the environment that we're keeping here is that like the stream state always has an input to give, essentially. So the way you kind of see the state evolution maps, which are like kind of like the types don't tell you that much, but what it actually says is that like when you do the operational semantics, like your state evolution map kind of like acts on exactly what you expect, essentially. So when you do an input, like when you like program asks for input, you just give the input and then apply that state evolution map on like the rest of the state of the stream. And then like when the program asks like gives an output, then you just like give the output to like the hidden state and then like apply the state evolution map. So how we then define a notion of program equivalence on this is again not super difficult. So like once we have like the thing on the just quantum computing. So without communication, the way we do this is kind of by merging all the branches with the same continuation and kind of discarding like everything that has like the same continuation. Discarding every classical information on like sort of the branch you add if you have the same continuation. And the way you can see this is by like looking at the quantification there. So like this whole statement is something like for all initial state and for all x, where x is kind of like the classical branch you're on, therefore like encodes the classical information. And with communication, you can just do the same thing, except we want to also quantify on the classical, like the I/O trace that your program gives. Yeah, sorry. So like here it just says for all x for all sigma prime, where the sigma prime is kind of like the I/O that happens during the execution of the program. And the reason why you have to quantify over this is just because like when you want to discard information, you need to sum over states that are like that, like sort of are like density operators on the same on the same Hilbert space. But then like like if you have different traces, but like the same continuation variable, but different traces, then like the shape of your hidden state might be different according to the stream, essentially. So right, this actually gives us like a sound, like so a model of the algebraic theory, like with the operational semantics and the program equivalence that we just defined. And the next step now is just to try to get a denotational semantics out of this. And the reason why this kind of would make sense is because like, recall that like when we did the program equivalence thing on the qubit quantum computing case, so like without communication, we could kind of just convert between the denotation and the operational semantics very easily. And here it's kind of not too different. So we consider like this map, which is the map that maps like the every initial state row to like its to like this thing, which is like the one side of this program equivalence, essentially. And if we consider what it might look like, again, sorry for the string diagrams, but if we consider what it might look like, so like on the bottom it's like kind of the input, on the top it's kind of the output. So if we consider what it might look like, here it's like something that kind of does one output and one input in that order. And like clearly we have like, so on the left we have something only like talking about the program state, on the right something talking about like the, like where you have the stream evolutions, and you have kind of things that send and receive like qubits. So unfortunately here, like this map still kind of depends on the stream, which is arbitrary, and we will kind of want to like have a university quantification over it. So what we do here is just we like remove the state evolution things, and what we have left here is like exactly a characterization of the map C, the denotation of C, but at stream like the denotation of C, like that goes to like continuation variable X, and that gives a stream like a stream trace of sigma prime. Now the issue is that like now the type of this map doesn't actually give the information of like the causal ordering of like the inputs and outputs. So all that we have to do here is just to like use the compact closure of that category, or like the Choi-Yamelkovsky, is that how you pronounce it? Isomorphism, by essentially bending all the input wires up, and now like on the output side we kind of just get like the causal ordering that we wanted, and the rest is kind of you just do a byproduct over it. So you just do a classical choice over all the possible stream traces and like the continuation variables, and this is kind of your denotational semantics essentially. So equivalently, you can see this as a Kleist arrow for this monad, and this monad is exactly the free IO monad on the category of CP maps, like DCPO completed because you need like infinite byproducts. So yeah, we get a theorem that says adequacy in full abstraction with respect to the operational semantics I just gave, and we get the full triangle-ish. So you can see that like here, the algebraic theory is only sound with respect to the semantics we have. So we don't have a notion of completeness yet. And so like as a first step for future work, we want to, well, essentially get completeness, but also see if we have like connections to other notions of sort of program equivalence that were exammatized like by similarity in quantum like process calculi, for example, because we are really considering a local sublanguage of quantum process calculi. And also we want to see if there are connections to high order quantum computing just by, because like when like the thing where you bend the wires up is kind of like a, like it's used, for example, in like giving a model for the like quantum lambda calculus. Right. So here's like a much longer form than like the 5-page abstract if you're actually interested in the details. And yeah, well, thank you. And that.
Any question?
do these theories account for just finite circuits, or can you account for things like loops as well?
Finite things. Sorry, it's all finite.
Okay.
Which is why it's like much simpler than
Have you thought about loops?
No. Who needs loops really?
Hi, nice talk.
Thank you.
Serious question and a facetious question. Serious question: is there some particular obstacle to completeness, or you just didn't have time?
My I had 3 months, so.
Okay, good luck. Facetious question: why apologize for using string diagrams?
Oh no, but like it's just like I've been told that like this workshop is supposed to be like sort of accessible to the wider PL community, etc. And like string diagrams for monoidal categories is like kind of it's very specific to sort of certain fields essentially.
Okay, very nice talk. I wonder how full abstraction was sort of easy-ish to come by. Full abstraction for PCF was an open problem for 20 years, and was really hard once it was solved. But here, okay, I know that it's not easy, but it's easy-ish. What is the core simple thing about your setup that makes it possible?
It doesn't have non-termination. It doesn't have loops. So like we're just modeling everything as it is essentially.
Very good. Okay.
Yeah.